serious coffee. So I need to do 3.1 again. Had problems with the streaming. Right, so here we've got a T-bar. And we've put a load in. It's actually coming this direction. Put a load in and we're twisting it. So our M has already been worked out for us. The M is 3,000 Newton meters. And we're being asked to find, what are we being asked to find? We've been asked to find the maximum compressive stresses, top and bottom. So what we're going to do here, this is just a standard problem that we did in the first year, where you have a T-bar. Where's the centroid going to be? Who knows? So the central will be somewhere or other, and you need to then measure the distance from the top to the top and the distance to the bottom. And you're going to use the engineer's bending equation. So use the first two bits to find what the stress is, top and bottom. The Y will be my top and bottom values. Here, I don't know the I at the moment. I don't know the Y top and the Y bottom values at the moment, so I need to work them out. A bit too close, I feel. Right, so what am I going to do there? So obviously I need to find neutral axis. So this is a standard first year type problem. So set yourself up some sort of table. What can we put in it? You can put in B's and D's. We can put in areas. We can put in the centroids for those particular sections. We can do the first area of moment. We could do the H, the distance from the distance, so modulus, so the distance from the centroid of that particular section to the neutral axis of the cross section. From that, I could find the parallel axis theorem component, and because we're doing boxy sections, BD to the power 3. So good plan for these type of problems is to work in, since we've got our geometry, it's all in millimeters. Good plan is to work in millimeters. So I've got 30, 40, this is my bottom part of my section, and then I've got 90 and 20. So that times that, fill it in. So that's 1800, and that's 1800, and 1200 there. The bottom one is, since let's draw this little geometry here, so bottom one is 30 and 40, and the top section is 90 across and 20 going down there. So I'm expecting it to be probably around here. The centroid of this T-beam. So the bottom one is going to have 20 there. Here we've got 40 plus half of this distance, that's 50. So now I can do my first area moments, and that works out to be 90. Oops, 90 there and 24, and they're both times 10 to the 3. In these things, try and identify a sensible value to be looking at things, so you can sort of take out your units. Now for my H, I don't know, I need to find my neutral axis, so that will be the sum of a y's divided by the sum of a, and that turns out to be 38 millimeters. So now I've got the 38 millimeters here. I can now take 20 away from 38, so that's 16. And I can take 50 away from 38, so that would be 12. Now I've got the area h squared, so I can fill in this box. So 1200. My h is 18 squared there, 1800, and my h is going to be 12 squared. These I can go back to these values in these boxes. So we've got 20 times 40 to the power 3 divided by 12, and here we've got 90 times 20 to the power 3 divided by 12. So if you want, just leave them, don't have to actually work out your numbers, and then use your calculator. Okay, so use your calculator and then plug in all this stuff here, okay, if you wanted to. So then we will find what I is. So that's going to be the sum of all the AH's and all the 1/12 BD to the power 3's. And cut a long story short, we get 868 times 10 to the minus 9 meters to the power 4. So when I work this out, I'll get the answer in terms of millimeters to power 4. So that'll be by something like times 10 to the 3. And then you obviously want to divide that by 10 to the 12, and you end up with that result there. So verify that for yourself, see if you're happy with that. So then move on to the next bit. So the stress to get to the top divided by I, and then we're going to have stress to get to the bottom divided by I. So the top bit, look at the diagram here. So the top bit, this is being stretched. So that's going to be a positive stress. So we've got 3000. And then we've got to say to ourselves, well, if this is the neutral axis, what's the distance to get to the top? Well, I now know that that's the neutral axis. So to get to the very top here, it's 60 millimeters. So this distance here to here will be 38, 22 millimeters. And to get to this distance from here to here will be 38 millimeters. So there are my two Y values that I need to stick in. So to get to the top, we need 22 millimeters. And we divide that by, work in SI units, 868 times 10 to the minus 9. And for the bottom one, I could put in a minus there, I suppose, 3,000. And that'll be 38. Divided by 868 times 10 to the minus 9. So stick those values in your calculator. And we're going to have a stress of 76 megapascals and minus 131.3 megapascals. 3 sig fig there, and I suppose to the one decimal place there. Okay. Now for the radius of curvature, so my T-beam is like this. Yeah, and I've got something turning here. So if I looked at it sideways on, I'm therefore expecting it to be doing something like that. Okay, so it's come off my page, but that would mean that I could then try and fit a radius of curvature here through this. A big circle will go through this section here. So we're expecting it to be curving a little bit, not too much. So therefore, the radius of curvature, the value for that is going to be, although it's not curving much, we are expecting a large curvature value. Does that make sense? So that value there is going to be very large, because trying to fit a circle through it means that our centroid has to be really far away from the beam. Okay. So it's hot in here. So we have we got the R, and so we go back to our engineer's bending equation. And say to ourselves, what bits should we use here? Well, it's not sensible to use the middle one. The why is that? Because I've derived the stress results, top and bottom, and I also derived the Y value after I found the, or no, actually no, I found the stress last, and then I sort of found the Y values sort of first, and then sort of in between I found the I value. So the most reliable data I've got is going to be my I, okay, because I found the stress last. So let's use the I and the M. So we're going to have M over I, and we'll relate it to the E and the R. So the radius of curvature will be, imagine that jumps up there. E and I like to be together, and the M comes down there. So R is going to be what? Okay, I've screwed that up. R goes up. No, I haven't screwed that up. I've done that perfectly fine. So what we're going to have, so the E is, what's he got? So you got 190 times 10 to the 9. And your I is this, 868 times 10 to the minus 9. Your M is 3000. What is that going to be? Yeah, get some decent light on that side, so let's put the calculator there. Move the lights around a bit. Could do with a light there. Right, so 190, that and that going to cancel. 2 times that by 868 divided by 3000. Ooh, got that right. So that's 54.3 meters. So big distance as we're expecting compared to the. Are we told the length? Not really, but we can sort of guess it's not going to be more than a meter or so. So, what about the last part? So the last part is asking for the radius of the anticlastic curvature. What's that all about? So imagine your beam. Like this. And we've worked out that it's kind of curvating around this direction. And we've got a curvature of 54.3 meters. And that's due to a direct, well in this case it's not a force, but a turning moment being applied here. So that's the dominant, that's causing the dominant stresses changes in my beam. And if I looked at my beam now sideways on, I would say that we've got sort of into the page, we have a stress of 76.6 megapascals at the top. We have a neutral axis, and then we've got a greater compressive stress of 131.3 megapascals at the bottom. Okay, so you can see this from this sort of sideways sort of bit of the diagram. Yeah, so this is going to get stretched out, and the bottom is going to get squashed in. So if this is getting stretched out, what's going to happen sideways on? And if this at the bottom, so this at the top, is that's getting stretched, so that's going to come inwards, and here this is going to get squashed. So when this gets squashed, and that's going to push it outwards. Yeah, so this gets it's going to get squashed this way, so it's going to get point outwards like that. So now take these, which ways we're expecting things to go. So we're expecting this to be moving inwards, getting squashed. Sorry, I've done this the wrong way around, haven't I? So, sorry, this is getting squashed, so it's going outwards, yeah. So, yeah, just need to follow my diagram. So this is going outwards, like that, on this section. And here, we're coming inwards. So if I imagine that I had little markers on my beam, so I had a marker here, marker here, marker here, marker here. Actually, I'll put my marker here and here because that will become more useful for me in a minute. So if I didn't have any load and I put these 6 markers here on the beam, what happens when I apply this load and I stretch the top off in this direction, compress the bottom in that direction? So for the top, the thing will be in the transverse direction, is that will get squashed in. So these markers will now move inwards. And then the little red dot will move in like that, and these will move in like that, because you can see what's happening on the top side. Here, however, this is getting squashed this side, so it ends up pushing outwards. So the markers now push outwards. So these ones here are of interest, the 4 markers in the middle, because if I try to draw a line through them when there's no load, the line goes off to infinity, i.e. my radius of curvature is going off to infinity. However, when I've applied the load, you can now see that the markers are going to converge to a point. Like that. God, this is going to get high, man. So we've now got a radius of curvature. So you've got 1 from this side here, and now you've got another radius of curvature kind of going off in this direction. Okay, is that making sense? My brilliant 3D diagram. So they are at right angles to one another, and also one's going downwards and the other one's sort of going up. And so this is what the anticlastic radius is. So next thing you've got to say to yourself, do I expect this radius of curvature to be bigger or smaller? Think about it. So you expect that if I'm pulling something one direction, it's going to come in at right angles, but a bit less. Okay, so that means that a larger radius of curvature means that we're getting less deformation. So therefore we expect a larger value. So all I do to find the radius of curvature, that's the anticlastic one, turns out to be that our stresses are going to be proportionate to the Poisson's ratio. So I just take my normal value and divide it by my Poisson's ratio. Okay, so that will give me a larger value, 54.3 divided by 0.3. So the last bit will be 181 meters. So trying to fit a curve around that particular section, it's going to be even further away. Right, so hopefully the streams have worked this time. Oh God, it took me 10 minutes longer as well.